Okay, welcome to AP Calculus, the fourth section of our homework problems from 4.3, where we're dealing with inverse trigonometric derivatives. As I've shown on the previous three videos to this, we should either know these, we should all be able to derive them. We've done that in class, even to the point where we can explain why this should be an absolute value of x, maybe a little bit tricky there. Hopefully as we use these, we get through enough practice problems that these start to soak in. So let's pick it up where we are just supposed to find the derivative. In this case, this would be dy ds, the derivative of function y with respect to variable s. And our secant inverse derivative involves this absolute value. Otherwise, it looks a lot like sine, but the x squared and the minus 1 are switched. So a lot going on here. So this is what the derivative would be if we were taking the derivative of just plain old x. Now, understand, we can put times dx dx here after we take the derivative, and it would just be times 1. But what we have to do, if it's not plain old x or plain old s in this case, is we have to treat it like a chain rule. So maybe you want to wrap parentheses so we can think of that as the baby function. So derivative of secant is 1 on absolute value of the argument times square root of the argument, all of it squared. Wow, it would be really easy just to square the 5s here, but it's, or just to square the s, but it's 5s squared minus 1 times the baby derivative 5. So at this stage we get 5 on square root, or excuse me, absolute value 5s square root 25s squared minus 1. So see anything that we can do with this? Well, this 5 is not contributing anything inside of this absolute value that's going to change it, whereas if I pulled the 5 out, 5 times absolute value of s is the same as absolute value of 5 times s. So this 5 can actually pull out of here and cancel, and we end up with dy ds equals 1 on, still need the absolute value, but the 5's cancel, and still need square root of 25s squared minus 1. And that is a back of book, likely to be a back of book answer. Pretty simplified. Yeah, we have a radical in the denominator, but if we multiply by top and bottom, it really it makes the numerator almost as bad as the denominator and doesn't really clean up the denominator that much. So again, as I often say, simplified in the eye of the beholder. If you don't match the back of the book, try to work to match it. Do whatever simplifying you think is appropriate first, check the back of the book answer, and then work to match it, just because we can benefit from the algebra practice, the trigonometry practice involved in simplifying. Okay, so cosecant's derivative, very similar to secant, other than it is the opposite of. So hopefully we get out of this one in about the same number of steps. So this is going to be a dy dx, derivative of function y with respect to x. And if this was plain old x, our derivative would be negative 1 on absolute value of x, but it's x on 2. If it was plain old x, it would be x squared, but it's x on 2, all of it squared, and minus 1. And if it was plain old x, I'd be done, but it's not. I've got an inside derivative, so I need the derivative of x on 2. I could have made that 1/2 at that step, probably should have. Okay, much like the last problem, I think I got room. I'll go ahead and write one extra step. So the derivative of x on 2 is the derivative of 1/2 x is just 1/2. So this is negative 1/2 divided by absolute value of x on 2. You may be able to see where we're going from this. All on x squared on 4 minus 1. The 1/2s cancel. This 1/2, just like the 5 over here, could come out. I need the x has to stay in absolute value, but there's no doubt 1/2 is positive. It can come out. So I get negative 1 absolute value of x times square root of x squared on 4 minus 1. Now I think there might be a good chance that that guy gets simplified a little bit here. And that is because we've got this whole compound fraction issue going on. And not only that, but the denominator's 4. So if I was to treat this as common denominators in here, this would be minus 4 on 4, so I'd get x squared minus 4 all on 4. That would be negative 1 on absolute value of x. The square root of 1/4 is 1/2. I can pull that out, x squared minus 4, and I can multiply top and bottom by 2. Sorry, didn't move that up for you. Let you have a second to get caught back up here. I pulled 1/4 out as 1/2, multiply by 2 on 2, and I get negative 2 over absolute value of x, x squared minus 4. We worked hard to get here. Let's write the answer the way it should look. dy dx equals, and I believe that is what our back of book answer will look like. Okay, let's continue on with number 18. First thing we might want to do with this is treat this as cotangent inverse of t to the 1/2. That may be helpful. Parentheses always helps me identify baby functions, so we're chain ruling this. This would be a dy dt equals cotangent's derivative. I like tangent and cotangent, maybe the best. Just negative 1 on 1 plus, don't think of this as x squared, think of it as the argument squared. And then if we have an argument, we got a baby function. We have an argument other than x. So negative 1 on 1 plus the argument squared. So this becomes negative 1 on 1 plus t to the 1/2 squared, but times this guy's derivative, times 1/2 t to the negative 1/2. Or let's see, the only thing from here that would go to the numerator is this 1. Negative 1 on, in the denominator, there's going to be a factor of 2, there's going to be a factor of square root of t, or t to the positive 1/2 if you like, and that's going to need to be multiplied by 1 plus t to the 1/2 to the second is just t. And maybe that would be a back of the book answer. Perhaps they write this as a square root. We would easily be able to get from here to here. Maybe they distribute this, make this 2t to the 1/2 plus 2t to the 3/2. I kind of suspect, since they started with the convention of square root, I kind of suspect they end with dy dt equals negative 1 on 2 square root of t times 1 plus t. That's my thought on that one. Okay, number 21, a little bit more going on. We actually had a problem that had a similar appearance to this back in number 6 earlier in this, and it simplified out quite a bit. Let's see what happens here. So I'm going to have to deal with secant negative 1's derivative. We'll talk about that, but I might, before I start finding derivatives, rewrite this as s squared minus 1 to the 1/2 minus secant negative 1 of s. So dy ds. See if I run out of room on this guy. So my derivative of this first term, it's a chain rule, 1/2, leave the baby alone to the negative 1/2, treat the baby times 2s, minus secant of s's derivative. That is not a chain with respect to s, so secant derivative is 1 on absolute value x times square root x squared minus 1. 1 on absolute value of s times square root s squared minus 1. So, wonder if anything good happens here. Let's take a look. 1/2 times 2 is 1. I get an s. On, I'm going to leave this as s squared minus 1 to the 1/2. Minus 1 on absolute value of s. Maybe I'll write this as s squared minus 1 to the 1/2 as well. And now I'm thinking about common denominators. And my common denominator needs a factor like this, needs a factor like this. Now, again, simplified in the eye of the beholder, But I also need a factor of absolute value of s if I'm going to smash these together, so I'm going to put absolute value of s here. And now I get s times absolute value of s, which is weird looking. Haven't seen a whole lot like that before. All over absolute value of s times s squared minus 1's square root. Can we clean this up anyway? If s is positive, this is just s squared. If s is negative, a negative value, then this becomes negative s times s. It becomes a negative value again. I think that's probably about what we can do this, unless we want to break it into a couple separate cases. So you can check back in the book. Maybe they end here without the absolute value, but I wouldn't be surprised, since we sort of almost had, we were very close to common denominators when we just had this and this. Wouldn't be surprised if they moved to that step. Okay, number 22. Rather deal with this one than this one, because this is going to be a chain. Not that big a deal. This one's going to be pretty straightforward. Minus, I better make sure if there's any distributing to do, I distribute. Okay, so this is going to be a dy dt. Oh, and I just said it earlier. We should wrap that up. Dy ds equals. This is a dy dt equals cotangent's inverse. Here it is. I know it's negative because it's a co. Negative 1 on 1 plus x squared. So that is negative 1 on 1 plus the argument, 1 on x squared, times x to the negative first's derivative. I'll leave that for another step. Minus tangent's derivative, just like this, is 1 on 1, positive 1 on 1 plus the argument squared. So I've got this. Looks like simplifying may be the biggest challenge here. Let's see. Negative 1, the derivative of negative x is negative x to the negative second. But negative x times negative 1 is x to the negative second. All on. Ooh, this might work out really nicely here. Let's see. 1 plus, I'll leave this as, make this maybe 1 on x squared, minus 1 on 1 plus x squared. And before I worry about common denominators, I'm going to bring this to the bottom. That's an x squared times quantity, 1 plus 1 on x squared. How about this? I think I see where this thing is headed. And I get 1 on x squared plus 1 minus 1 on 1 plus x squared is 0. Did I put dt up here? How silly. Dy dx is 0. And you say, can that possibly be true? Can that possibly be a constant all the time? Well, why tangents switch y's and x's around? So tangent inverse, we're putting in ratios here, x on 1. That is the same exact, here we go, cotangent. This is taking a ratio of sides and getting out an angle measure. This is taking a ratio of sides and giving out an angle measure. But cotangent is adjacent on opposite. This is opposite on adjacent. These are the same angles. This is like theta minus theta. I wish we would have stopped and analyzed that one for a little bit. So not surprised that we end up with 0 on this. Okay. So that gets us through number 22. We'll have a further video on this as we move forward. I believe there's a few more problems from this assignment, but we're going to jump a little bit. But I'm going to stop this one at that point.